Hello, this is Mr. Hilliard. This is a video lecture for Unit 6, Lesson 3. We'll be graphing logarithmic functions. Very important that you understand how to graph exponential functions before you do this. So if you're still not quite sure about that, go back and review that. We suggest doing it before this video, if possible at all, before watching this. So make sure you understand the day one lesson classwork first. All right, so we're graphing log functions. We're finding properties of log functions, analyzing graphs. Okay, so first we're going to graph a log function. The big thing with graphing a log function is finding where the asymptote is. Now, remembering that a log function is the inverse of an exponential function is imperative. Okay? Remember, the asymptote for the inverse of an exponential function, the asymptote for an exponential function was x equals some value, called c. Okay? So inverses, x's and y's switch, right? X switches with y switches with x. So if the equation of an asymptote for an exponential function is x equals some number, the asymptote for a log function is going to be y equals some number. So it's going to be a vertical line. All right, so instead of a horizontal asymptote, it's a vertical asymptote. That is very important. We're going to start every graph and figure out where the asymptote is. And you should be able to do that without actually graphing it. Okay? So, since the log is the inverse of an exponential function, the asymptote for an exponential was y equals 0. So if there are not any other shifts, the asymptote for a log function is going to be x equals 0. That's where it's going to start. That's any parent function you have, the asymptote is going to be x equals 0. And we'll talk about shifts in a minute. All right? So to do the rest of this graph, we want to convert this to exponential form. Not find the inverse. Just convert to exponential form. So what we do is we say 2 to the y equals x for this graph, for this function right here. All right? For any parent function, the domain now is determined by where the asymptote is. That's why the asymptote is very important. So the domain now starts at 0 and goes to positive infinity. And the range is negative infinity to positive infinity. You should notice that these are the opposite of exponential functions. The domain became the range, and the range is the domain from exponential to logarithmic. Okay? So now you have this basic information. We can sketch the asymptote. So x equals 0, vertical asymptote. Make a table of 3 parent points. I have parent in parentheses here because there's not one parent function for logs, the same way with exponentials. Okay? So by parent points, I'm taking this exponential form, I'm making a table of 3 values, but I'm starting with y. Okay, since it's the inverse of exponentials, I'm starting with y. So I want to see what x equals when y is 1, when y is 0, and when y is negative 1, when y is 0, and y is 1. All right? So plug negative 1 in for y. Okay? So 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. You're going to start any graph of a log function with these 3 points. Okay? It's going to change if the base is different, but this is where you're starting. And then you'll apply any shifts if there are. All right? So let's just plot these points. So 1/2, x equals 1/2, y is negative 1, about right here. X is 1, y is 0, x is 2, y is 1. Now, most of you are thinking, Mr. Hilliard, that's just a straight line. Well, technically it's not. If it was a straight line, it would go through the point 0, negative 1. It's a curve, okay? All we want you to do for these graphs is to plot 3 points But then make sure you understand the concept that the graph is going to approach the asymptote, but not touch it. Now, if your graph touches the asymptote, it's fine as long as it's not way off to the side. Okay? And as long as you understand in this direction, it's curving that way. This direction is here. That's the graph of a log function. That's the parent function, log base 2 of x. Log of 2. Log base 2 of x. Okay? So this is the graph of that function. Now, let's look at the end behavior. So this is a little different. The graph is always going to approach the asymptote. So when we can't really say x approaches negative infinity, because it never will. Not for a log function. Okay, not unless it's reflected. We won't do that. We won't reflect it over the y-axis. Okay? If it were, it could go to negative infinity, but everything we do is going to go positive. So x is never actually going to approach negative infinity. X will only approach the asymptote. F of x, in this case, will approach negative infinity. All right? As x approaches positive infinity, f of x will also approach positive infinity. Okay, that's your end behavior. So this is different. What we may ask you is, we'll give you this part, but we'll ask you the part, we'll say, okay, what does this approach in terms of as it approaches the asymptote? Okay, so I'll do one more down here, and you guys will practice the other two. All right? So these have transformations to them. So you still want to start with, what I mean by the parent function here is we just say log base 3 of x. Okay, we're going to start with that. We change that to exponential form. So that's 3 to the y equals x. You're going to do your x's and y's. Start with y. Y negative 1, 0, and 1. So plug negative 1 in, you get 1/3. Plug 0 in, you get 1. Plug positive 1 in, you get 3. So these are our starting points, and then we'll apply the transformations. With logs, same type of deal as we've done before. This part here, this red circle, is the horizontal shift. Okay? -1 means to the right one, +1 would mean left one. Over here, in the box, +2, that means we're moving up 2. If it was -2, it would be down 2. All right, plot your quote-unquote parent points first. So you do 1/3, -1, about here, 1, 0 here, the 0.31 is here. Okay, just start with those. Okay, wasn't following my own advice, and I never graphed the asymptote. Okay, so you should be able to graph the asymptote or plot or find the asymptote first. Given that x minus 1 means that the graph is shifted to the right one, everything shifts to the right one, including the asymptote. All the points of the graph and the asymptote shifts to the right one. So a horizontal shift for a log function is going to determine the asymptote. Okay? So it shifts right 1, so that means the asymptote is going to be at x equals 1. Okay? So you should do that first. Okay, sorry about that. So you plot do your asymptote first, find your 3 parent points, okay? And then apply your transformation. So every point moves to the right one and up 2. So right 1 up 2 is about here. Right 1 up 2 for this one is there. For the third point, right 1 over 2 is here. Okay? Your asymptote is x equals 1. This is what I kind of I mean about how the graph is going to look. It might be hard to draw it without it physically touching it on your graph, but as long as it looks like you're trying to keep it from touching the graph, I'm not going to get too technical about it. We need to make sure you realize that the graph doesn't cross the asymptote. All right? So, what is the domain? Well, the domain is determined by the asymptote. Look where the asymptote is. Okay? It's just 1, 2, infinity. The range for any exponential, for any log function, the range is going to be negative infinity to infinity. Now, end behavior. So, like I said before, it's never really going to approach negative infinity. Okay? It approaches 1. But f of x will go to negative infinity. This is a typo here. This bottom one should be positive infinity. As x goes to the right, the graph will also go up. Okay, so try the other two, and I'll have your graphs and the blanks filled in when you come back. All right, so for you have ln of x plus 2 minus 1. So remember, ln is a natural log. It's the same thing as saying log base e. All right? So your exponential form would be e to the y equals x. You see the points there. There's your graph, the main range. Again, you can adjust the values there for the end behavior. All right? So the key thing is going to be, well, Mr. Hilliard, I'm having a hard time getting the graph to look exactly right. Well, if you have the right points listed here, okay, and you draw your graph and you're trying to go through those points, that's what we care about. That's what we want to see. Okay? So you see where your graphs are, you see where your asymptotes are. That's the big thing. Again, the asymptote is extremely important for logarithms. All right? So let's move on to the next page and talk about just use the function to find these properties. So again, you know the range for any log is going to be negative infinity to positive infinity. The asymptote is determined by the horizontal shift. This is your horizontal shift. X plus 5 means left 5. Well, if the whole graph moves left 5 units, the vertical asymptotes move from x equals 0 to x equals negative 5. All we need there is that equation. That's what we want. We want the equation of x equals some number for logs, y equals some number for exponentials. All right? And so the asymptote will tell you what the domain is. It just goes from negative 5 to positive infinity. All right? So try the other two, and I'll have the answers for you when you come back. All right, so all you're doing is looking at that horizontal shift, find the asymptote. Use that to set your domain, and your range is always going to be all real numbers for log functions. Okay. So that's given the function. Let's look at a graph. Okay, this should be easier. Okay, your dotted line there is your vertical asymptote. Okay, now you won't have to look at a graph and give us the equation. There's just too many issues with that. What you will need to be able to do is compare a log graph to the graph of an exponential. Okay, so you should be able to tell the difference between those two. Again, the big thing is look where the asymptote is. If it's a vertical asymptote, it's a log. If it's a horizontal asymptote, it's a exponential. Okay? So, for this first one, you can see that the asymptote is at x equals negative 2, which means my domain is negative 2 to infinity, and my range is negative infinity to positive infinity. So again, the graph cannot approach negative infinity because it stops. It won't ever cross that asymptote. It can't. There's no value for x you can plug in. There's no value for y you can plug in to get a value for x less than that. So it only approaches negative 2, but goes down to negative infinity, or approaches negative infinity as it goes down. Okay? As it goes to the right, as x goes to the right, the graph also will go up. Okay? So let me make this change here. So try the graph to the right, and I'll put the answer up for you when you're done. All right, so pretty easy, right? Because the asymptote didn't move at all. Now, what I would hope that you could see is that the graph on the left was a horizontal shift, right? Because the asymptote moved. The graph on the right is a vertical shift. The asymptote didn't move, but you can see the graph went down. You should be able to recognize the graph went down. Now, you might not be able to figure out exactly where it is, but you can tell what kind of shift it was. All right, so something to keep in mind when we ask you to start comparing graphs of exponential functions and log functions. Okay, so when you guys come to class, I'll have a handout for you for classwork. We'll do a little bit of stuff for the graphing of logs. We'll spiral some stuff with the exponential graphs. Ask you to compare and contrast and evaluate different graphs. You'll have a quiz next time on graphing, exponentials, logs. Not for this class. For day 4, you have a quiz on graphs of logs, graph of exponentials, and evaluating logs like we did in day 2. All right, so be sure to write down any questions you have and bring those to next class. We will see you then.